Our second chapter involves the chemical level of organization. This is the smallest level of organization that we will be examining in this class. Basically, this chapter covers the chemistry you need to know for biology. Our objectives here are to review the language and fundamental concepts of chemistry, how matter is organized, including molecules, compounds, and mixtures, to review energy, chemical bonds, and chemical reactions, and review, compare, and contrast organic and inorganic compounds. Our first section is on elements and molecules, so just introducing these two things. Matter is anything that has mass and takes up space. Mass is the amount of matter a substance contains, whereas the weight of a substance is the force of gravity acting on the mass. Since we primarily will be doing our biology on Earth, the weight will always be the same, so the weight and the mass will always be equivalent. The mass and weight change when you're not on Earth. So if you're doing some space physiology, you might have to look into mass versus weight, but those terms are going to be pretty much the same thing in our class this semester. So matter can exist in three different forms: a solid, a liquid, and a gas. Chemical elements are on the periodic table, and all forms of matter are composed of chemical elements. So the element is the simplest form of matter with unique chemical properties. The atomic number is how we denote each element, and that is the number of protons in the nucleus. So every element has an atomic number, and that atomic number is how many protons are in the nucleus. 26 elements have a biological role, with 4 major elements making up about 96% of our body weight. Those 4 major elements, which you should definitely know, are oxygen, carbon, hydrogen, and nitrogen. So you can see that 96% of our body is our major elements: oxygen, carbon, hydrogen, and nitrogen. Then we have some lesser elements that we'll talk about pretty frequently. So calcium, you're going to find that in our bones, as well as phosphorus, potassium, sodium chloride. Those are all important electrolytes. Sulfur is going to be incorporated into some proteins and other large molecules. And then magnesium and iron are both important cofactors with enzymes. So we'll see most of those throughout our semester. And then we have a few trace elements where we just need a little tiny bit of them to function properly. And you can look at those indicated in that purple color there. So minerals are inorganic elements absorbed from the soil by plants. We then eat plants or eat things that have eaten plants, and we are able to get those minerals into our body. They equal about 40% of our body weight, and they're going to be very important in structure. So our teeth, our bones, calcium is one of our important minerals, and also in enzyme function. They function as cofactors. And things like magnesium and iron are important cofactors in enzymes so that we get the enzymes functioning properly. So molecular and structural formulas are important to understand. The molecular formula simply tells us what elements and how many elements of each are in a molecule. The structural formula tells us what shape that molecule is in. So it may be that we have 2 molecules with the same molecular formula, but different structural formulas. Those things are called isomers. So the same components, but we've put them together differently. For instance, if you make pancakes, you get a pancake, but the ingredients are the same as if you make waffles, but we've put them together differently, so one's a pancake and one's waffle. That would be an example of isomers, the same recipe but different structures. So This becomes important when we start looking at what chemicals actually do. So ethanol is very different than ethyl ether, but if we look at their molecular formulas, they are the same. They both have 2 atoms of carbon, 6 atoms of hydrogen, and 1 atom of oxygen. But in ethyl ether, the oxygen is in between the 2 carbons, whereas in ethanol, the oxygen is on the end and the carbons are next to each other. This makes a big difference in whether or not this substance can poison you or not. So that would be really important to know the difference between these 2. So just understand that some of the molecules we'll be looking at have similar or the same molecular formula, but their structural formula is different. Glucose and fructose are a good example of this. So now we're going to discuss how ions or how elements stick together. One way elements can stick together is through ionic bonds. When 2 elements are stuck together, we call that a chemical bond. The first bond we're going to talk about is an ionic bond, and this is how sodium and chloride are bound together in salt. Sodium tends to donate an electron because its valence shell, that outer shell, only has 1 electron in it, and it gets lonely and wants to go hang out with some friends. So it's going to pop off. Chlorine, on the other hand, has 7 electrons in a shell that holds 8. So it prefers to adopt an electron so that it fills up that valence shell and everybody is happy. So that electron will go from sodium to chloride, and then sodium will be slightly positively charged because it's given up a negatively charged electron, and chloride will be slightly negatively charged because it has gained an electron. Because opposites attract, sodium and chloride are going to be attracted to each other and form an ionic bond. So an ion is a charged atom, and ions with opposite charges are attracted to each other. An anion is capable of conducting electricity, and it is the atom that has gained the electrons. So in this example, chloride would be the anion, the negatively charged ion. The cation is the atom that has lost an electron and has a net positive charge. In this example, that would be sodium. So many of our ions, or salts with ionic bonds, like sodium chloride, are going to ionize in water. What that means is that the ionic bond breaks when it is immersed in water. So the sodium and the chloride separate, and they just float around in the water by themselves. So when you add salt to water, it becomes salt water, and those 2 things dissolve or ionize. These salts that ionize mean that the water in our body can conduct electricity. So these ions in our body fluids are what help us conduct electricity. So electrolytes, sodium, chloride, potassium, magnesium, calcium, those are all electrolytes. They're very important. They allow us to have chemical reactivity, so they're important in chemical reactions. They have osmotic effects, so that means they influence water movement in and out of the cells. And they have electrical effects on nerve and muscle tissue, and we'll learn about how nerve and muscle conduct electrical impulses later this semester. So imbalances in electrolytes can cause cramps, brittle bones, coma, and even death. So electrolytes are pretty important. The next type of bond we're going to discuss is covalent bonds. Covalent bonds are when 2 atoms share electrons. So one doesn't give it up and the other one takes it. They share. We can have single, double, and triple bonds, and that just indicates how many pairs of electrons are being shared. In the top example, 2 nitrogen atoms are sharing 3 pairs of electrons, and that will result in a triple bond. Underneath, we have 2 oxygen atoms that are sharing 2 pairs of electrons, and that gives us a double bond. Covalent bonds are much stronger than ionic bonds. We have two types of covalent bonds. One is nonpolar. This means that the shared electrons spend equal time around each nucleus. So we don't have an area that's more negative or an area that's more positive. It's very uniform in its charge. These are going to be the strongest of all bonds. Nonpolar covalent bonds are the strongest. Polar covalent bonds are the second strongest. These are when the molecules have covalent bonds, but there's a more negative portion of the molecule and a more positive portion of the molecule. So then where the electrons spend more time ends up being slightly more negative. Water is a great example of a polar covalent bond. The electrons spend more time around oxygen, therefore the red oxygen molecule is slightly more negatively charged, and the blue hydrogen atoms in that water molecule are slightly positively charged. So you have an area that's more positive and an area that's more negative, and that's a polar molecule. Hydrogen bonds are when other atoms associate with a hydrogen atom. It is the weakest bond and there's no sharing of electrons. It's an attraction between polar molecules. So this is what causes surface tension in water. So the partially positively charged hydrogen ion is attracted to the partially negatively charged oxygen atom, and so our water will arrange itself so that the hydrogen atoms from one water molecule face the oxygen atom from the other water molecule. Next, we're going to discuss chemical reactions, so how we create and break bonds.